So next, the per unit system for three-phase transformer. The per unit system of a measurement in a single-phase transformer can also be applied in a three-phase transformer. In the chapter 4, we talk about the per unit system as well. Then the two base quantity need to be selected. Same, two base quantity need to be selected to define a given per unit system, usually a voltage and power or a current power. So per unit in a single phase transformer is for example like this, like the P base, Q base, or S base, V base equals for example S base equals to V base times I base, or Z base equals to V base divided by I base, Y base equals to I divided by V, Z equals to V squared divided by S. All of them can be applied to three-phase system on a per phase basis. For example, given S base is total base VA of the transformer bank, the three-phase transformer bank, then the S for one phase base is the base VA of one of the transformer. It becomes uh, S for one phase base is S base divided by 3 lor. Then my I phase base is S1 phase divided by V phase. Then I phase equals to S base divided by 3 times V phase. First of all, we only need to change this into one single phase. Then the rest will be the same. Winding are connected in a delta. The V line base equals to V phase base. And then winding are connected in Y. The V line base will be equals to SUT3 V phase base. So as long as a single phase transformer and a three phase transformer, the what we call the basic is strong, then we can apply the same things here. Or the I line base equals to S base divided by SUT3 V line base. Example, we have a 50 kVA. Now the delta Y distribution transformer has a resistance of 1% and a reactance of 7% per unit. 1% means 0.01, 7% 0.07. So what is the transformer phase impedance referred to the high voltage side? So this is three-phase transformer. First of all, we need to convert into single phase, pick up to one phase, and then we put in a single phase equivalent circuit. Calculate this transformer voltage regulation at a full load and a 0.8 power factor lagging using the calculated high side impedance. Calculate this transformer voltage regulation under the same condition using the per unit system. So what is the transformer phase impedance? So from the high voltage side of this transformer has a baseline voltage of 13,800. You see, this one is 13,800. So now we need to choose two things. One is the voltage, one is a S, apparent power. So we choose the V base as a 13,800 and then apparent power 50,000. So this is the Z base. Z equals to 3V squared divided by S. Then the per unit impedance is a Z equivalent is a 0.01 plus J 0.07 per unit, Y plus, because this is lagging, reactance. So the high side impedance will be, we use a per unit times a Z base. This is the high side. Okay? Because all of here is referred to the high side, and then when we times to the per unit, it becomes high side. So calculate the transformer voltage regulation at a full load and a 0.8 power factor lagging using the calculated high side impedance. So when we want to talk about voltage regulation, first of all, we need to have a circuit, equivalent circuit. Okay? Then, but here, I think they did not mention the equivalent circuit, if not mistaken. Yes, it's here. So we will use a full load minus no load times 100%. Actually, this is the same. Full load minus no load minus full load divided by full load times 100%. How to get this one? We need to find our this one we so called the phasor diagram. So by using the phasor diagram, V phase primary equals to A times V phase secondary plus I phase times Z equivalent. And actually this is come from a high side equivalent circuit. So when we talk about high side equivalent circuit, okay, high side equivalent circuit, we have this. Okay, so we have our V phase P, we have our I phase P, then this is our Z equivalent primary side, then this is my V secondary, refer to primary side, which is A V S, right? This is in the phase phase. Then this is my I phase secondary side, refer to primary, okay, which is I secondary phase divided by A. Okay, so when I find the voltage across AB, okay, this is my B phase primary side, which is here. Then my A B phase secondary side is this one, plus the voltage drop across here, which is I phase times R equivalent, X equivalent. So this is already calculated in front, then we need to find I phase. So go back. So my I phase is, using this equation, I can find my ampere. So I substitute inside, okay, and then anything else? The rated voltage on the secondary side of the transformer is this one. When referred to the high side of the transformer, the voltage becomes AVS 13,000. Assume the transformer secondary is operating at the rated voltage and current, find the resulting primary phase voltage. So this one we already have, which is 13,800, and then R equivalent is calculated 11.4 of here 11.4.2, 4.2. Then X equivalent is 800, this one 800, and then I need to find my I phase. So first of all, I need to know what is the power factor. So they say that it is at a 0.8 power factor lagging. So which is, when we find the angle of the degree, it becomes negative 36.87 with 1.208 ampere. 1.208 ampere. So we put here, then we know that this is no load. This is full load. So this is no load. No load is a 14,000, 14506 minus 13800 divided by 13800 become 100%, become 5.1%. So this is how we find the voltage regulation. Every time when we want to find the voltage regulation, we need to find a friend. The friend is a phasor diagram. So this is the phasor diagram. When you form the phasor diagram, we need to know the circuit. Well, from the circuit, we need to know either it refers to the primary side or the secondary side. Then we go to find each of the parameters. Reverse engineering. Then we need to calculate the transformer voltage regulation under the same condition using the per unit system. Same as well. When it is per unit system, it becomes 1. Because 13,000 divided by 13,800 divided by 13,800 becomes 1. Then we find this is given, this is 0.8 power factor. Then the current also 1. Yeah, because we use base, you see this one calculated, but our base unit is also 1.208, so it become 1. Then put inside. So this is a full load, this is no load, this is full load. So 1.051 minus 1 times, it will become 5.1%, which is the same as this one. Okay. So next we'll talk about the standard terminal markings. So single phase transformer, the polarity of a transformer can be shown by the means of the dots. Remember the importance of the conventional dots in the chapter 4 that we mentioned before. On the primary and secondary terminals, the terminals are designed for the symbol H1 and H2. H1 high voltage lah. X1, X2 are the low voltage. By convention, H1 and X1 have the same polarity. Polarity means the dot side. The polarity is known when the symbol H1, H2, X1, X2 are given. It is common practice to mount the 4 terminals on the transformer tank in a standard way so that the transformer has either additive or subtractive polarities. If we know the power transformer has additive or subtractive polarity, we do not have to identify the terminals by symbol. So additive polarity H1, X1, H2, X2. Subtractive polarity H2, X2. Subtractive polarity is standard for all single-phase transformer above 200 kVA, provided the high voltage winding is rated above 8660 volt. All other transformers have additive polarity. Three-phase transformer. The high voltage terminal of a three-phase transformer are marked H1, H2, H3, and the low voltage terminal are marked X1, X2, X3. So if the primary and secondary winding connected YY or delta connected, the voltage marked terminals are in phase. So EH1, H2 is in phase with the EX1, X2. Same as well, H2, S1, X2, X1, H1, X3, X1, X3. If the primary and secondary winding are connected Y delta or delta Y, the results 30-degree phase shift between the primary and secondary line voltage. So the internal connections are made so that the voltage on the high voltage side always lead the voltage on the low voltage side. Okay, for the Y delta, delta Y lah. So EH1, H2 or EX1, X2 are lead by 30 degree. Lead by 30 degree, 30 degree. Then we go to transformer nameplate. So have a look on the, see this one is actually okay. A typical nameplate three-phase from a distribution transformer is shown like this. This is a product from a General Electric. We know that this is three-phase class A 75 kVA high voltage. See nothing here. So we have a 95 kilovolt for the high voltage winding. Low voltage winding is a 30 kilovolt. Interiors 370 pounds. Tanks 1100 pounds. Liquid 1300 pounds. Total is 2770 pounds. Then impedance is 3.15%. So this connection will be high. You see, high voltage is a delta connection. Low voltage is the Y connection. And then we have we still can tap it tap. So this is how we see you see this one delta connection H1, H2, H3. Then the Y connection will be X1, X2, X3, and then this is the common neutral one. Okay, then same as well, General Electric 750 kVA, and the details. And then this is YY connection. So high voltage Y, low voltage also Y. So we can tap in between. Then there's a common node for the neutral wire is connected to the common point of the secondary side. Then so the information on the nameplate, we have a rated voltage, rated kVA, rated frequency, transformer per unit series impedance, voltage rating for each step on the transformer, wiring schematic of the transformer, transformer type of that designation, references to each operating instructions. So additional information for the typical nameplate of a single phase transformer. This is single phase. We have a H1, H2, we have a X1, X4. Then this is additional one. Okay, so volts, if let's say we tap X1, X3 or X2, X4, X1, X3 or X2, X4, it is 120. If we tap X3, connected lah, we connect X1, X3 together, and also X2, X4 together, it becomes 120 volt. And then if we connect X3 and X4, it becomes 240. Okay. Next we'll talk about efficiency and transformer cooling methods. To prevent rapid deterioration of the insulating materials inside a transformer, adequate cooling of the windings and the core must be provided. Indoor transformer below 200 kVA can be directly cooled by the natural flow of the surrounding air. Indoor transformer below 200 kVA. So this is one of it, the ventilating louveaus. Louveaus. The heat will come up from this hole. We call the louveaus. For indoor transformer below 200 kVA too, the metallic housing is fitted with the ventilating louveaus so that convection currents may flow over the windings and around the core. Convection means released by convection mode. Larger transformer can be built the same way, but forced circulation of a clean air must be provided. Forced circulating clean air is some sort like we have a pump or the water fan like this. Such dry type transformers are used inside the buildings, away from hostile atmospheres. Distribution transformers below 200 kVA are usually immersed in a mineral oil and enclosed in a steel tank. Oil carries the heat away from the tank, where it is dissipated by radiation and convection to outside air. Oil is much better insulated than the air. That's why we use oil. So one of the examples like this is a small radiator. As the power rating increases, external radiators are added to increase the cooling surface. This is the radiator of the oil fuel tank. For still higher rating, cooling fans blow air over the radiator. If let's say we need a faster cooling method, we put a fan blow on the strip. We call it a cooling radiator. For transformer in the megawatt range, cooling may be affected by oil-water heat exchanger. This is another type. Then external radiator or the okay. And then we have a cooling fan. Then this is heat exchanger, which is with the oil and air. Some big transformers are designed to have a multiple rating depending on the method of cooling used. A transformer may have a triple rating of like this: 18 kVA, 18 megawatt, 18 mega ampere, 24 mega ampere, 32 mega ampere, depending on whether it is cooled. So 18 mega ampere VA, but usually by the natural circulating air. 24 mega VA is come with a forced air cooling with a fan, we call FA. Or 32 MVA, we use by forced circulating of oil accompanied by forced air cooling FOA. Transformer cooling classes along with their designation prior to this standard. Or C57.12 12.00. AA type for dry type self-cool. AFA is for dry type forced air cool. Oil immersed self-cool. Oil immersed self-cool or forced air cool. Oil immersed forced air cool or forced air cool. Forced oil air cool. So different type. Different type depends on how big is the transformer. The temperature rise of a dry type transformer may be as high as 180 degrees depending on the type of insulation used. Another one is a transformer in a parallel. Sometimes we need to connect it in a parallel if let's say we do not have extra money to buy a new unit. So when the growing load eventually exceeds the power rating of an installed transformer, we sometimes connect to a second transformer in parallel with existing one. The requirement for identical angular displacements must be met for paralleling any three-phase unit and or any combination of banks made up of a three single-phase unit. Zero-phase displacement for YY and delta connection. Because YY and delta will be zero-phase since displacement is the same. This may be parallel. A YY and delta transformer, zero displacement cannot be parallel with delta Y or Y delta. Y delta or delta Y that has 30 degree of displacement. This will result in dangerous short circuit. So this is a possible connection of either Y delta or delta Y. For example, this one would be H1, H2, H3. This is Y connection. YY connection. Connection of single phase transformer for three-phase operation. This is actually represented by this one. Either it's a delta delta, YY, delta Y, Y delta like this. So it can be operated parallel connection of a three-phase transformer. Low voltage side, high voltage side. Transformer A, if let's say delta with delta, we can parallel with delta with delta. Transformer A if a Y and Y we can connect it with a Y and Y. Delta delta can be connected to the YY. YY can be connected to the delta delta. Okay, so forth. Inoperative, which is cannot be done. If let's say my transformer A is a delta delta connection and I want to try to connect parallelly with delta Y, it is prohibited, cannot. Okay, same. For example, Y delta, then I cannot connect to the YY. So in making parallel connection of a transformer, polarity marking must be followed, regardless of whether transformers are additive or subtractive. Connection of a terminal must be made according to the marking and according to the method of connection. Next, we'll talk about the load division between the transformer in a parallel. Transformers are suitable for parallel operation when their turn ratio, percentage impedances, and the X over R ratio are the same. Connecting the transformer when one of these parameters is different will result either circulating current or unwanted current division. Both of these situations lower the efficiency and reduce the maximum amount of load the combined transformer can carry. Typically, transformers should not be operated in parallel when the division of load is such that with the total load current equal to the combined kVA rating of the transformer. One of the transformer is will be overloaded. The no load, then second condition is should not be operated as well. The no load circulating current in any transformer that exceeds 10% of the full load rating. Then the combination of the circulating current and the full load current exceed the full load rating also cannot. So overall connection summary of a different connection type of a parallel transformer can be put it in this chart. And then okay. Equal impedance, equal ratio, same kVA. The standard method of connecting transformer in parallel is to have the same turn ratio, percent impedances, and kVA rating. Parallel is typically accomplished by maintaining a tiebreaker in the normally closed. Normally closed means it is connected position. Connecting transformer in parallel with the same parameter result in equal load sharing and no circulating current in the transformer windings. So for example, this is 2 MVA with a 13.2 kVA, 480 volt, 5.75% of the impedance. This is the same, and then it can be parallel. Okay, it can be connected. It can be seen that using below equation, if the percentage of typical single phase parallel operation. So I have a transformer 1, transformer 2. I connect the H1 and H1, H2, H2, X1, 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 X2, X2. So it can be seen by using the below equation, if the percentage impedance in each transformer are the same, there will be equal current division. And the load sharing of each transformer. For example, I have a transformer 1, transformer 2, Z1, Z2, the same. So I1 is here, I2 is here. This is my IL, load source. So IL equals to I1 plus I2. Current division rule. So I have this one. Then, since the current has a direct relationship with the kVA, substituting kVA for current into the above equation, the same comparison can be made using the load kVA as shown in the equation like this. And this one. The above equations are arithmetically correct only when the ratio between the reactance and resistance of the transformer are equal. In other cases, the sum of the individual load current will be greater than the current in line. So this is one of our example. Have a try. Then equal impedance, equal ratio with different kVA. Although it is not common practice for new installation, sometimes two transformers with different kVA and the same percentage impedance are connected to one common bus. In this situation, the current division causes each transformer to carry its rated load. There will be no circulating current because the voltage are the same, just different kVA. Okay, this is another example. What if an unequal impedance? So this is a bit difficult. A bit dangerous. Frequent in practice, engineers are trying to enhance their power plant or the plant system by connecting existing transformer in parallel that has the same kVA rating but with different percentage impedance. This is common with the budget constraint limit. If let's say we don't want to change a new one, to the purchase of a new transformer with the same parameters. What the engineer needs to understand is that the current divides in inverse proportion to the impedance. Larger current will flow in a smaller impedance. Thus, the lower percent impedance transformer can be overloaded when subjected to heavy loading, while the other higher percent impedance transformer will be lightly loaded. That's the consequences. Equivalent circuit are parameter using open circuit and short circuit test. I will not further explain more on this one because we already talked about this in a single phase transformer very detailed. So I will just bring through this one. The major item to be considered is a 4 copper losses, eddy current losses, hysteresis losses, leakage flux, and then we model it in equivalent circuit, convert into equivalent circuit. The most important is we convert the three phase to single phase first, and then it will come to the equivalent circuit, and then approximate equivalent circuit of a transformer. Actually, the same. For here is referred to the secondary side. For this one, it referred to the primary secondary side. This one is referred to the primary side from secondary. This one is referred to the primary side from referred to secondary side from primary. So we have two tests. One is open circuit test. We want to find the we can find the power factor. We also after the measurement we can find our this one admittance. From the admittance we can find our equivalent circuit, and then short circuit test. Short circuit test. Short open circuit test for us to find the excitation branch. Sorry, not equivalence. This one. For the short circuit test, we'll use to find the equivalent resistance, equivalent impedance. For example, this one. So actually, we can find further details in chapter 4, single phase transformer. Then same as well, transformer voltage regulation and efficiency. We can take it from a single phase transformer as well. We would similarly, voltage regulation is equal to voltage on the secondary with no load minus voltage secondary with full load divide by voltage secondary on the full load times 100%. So when we talk about voltage regulation, we need to know the phasor diagram from this equation. Transformer efficiency, same as well in a single phase transformer. Have a look, yeah. We need to find when we want to find the efficiency, it's P out divided by P in. P out equals to P in equals to P out plus P loss. So P loss has a copper loss and P core loss. Then we use this equation to find the transformer efficiency. Okay, next, the final is the instrument transformer. Instrument transformer are used for measuring the voltage and currents in electrical power system, and for power system protection and control. Where a voltage or current is too large to be conveniently used by an instrument, it can be scaled down to a standardized low value. There are two types of instrument transformer. One is a potential transformer, another one is a current transformer. Potential transformer is used to measure the voltage. Current transformer is used to measure the current. Potential transformer is used to step down the voltage of a circuit to a lower value that can be effectively and safely used for operation of instruments such as ammeters, voltmeter, wattmeters, and relay used for various protective purposes. Current transformer is used to step down the current of a circuit to a lower value and is used in the same types of equipment as a potential transformer. This is done by constructing the secondary coil consisting of many turns of wires around the primary coil, which contains only a few turns of wire. In this manner, measurement of high value of current can be obtained. So the potential transformer, current transformer can be do like this. So if let's say I want to know the voltage, this is a 13.8 kilovolt. I want to know in measure in 120 volt VAC. So what I need to do, I need to connect a potential transformer. So many coil here, less coil here. So I connect it, and then I step down to the lower voltage. I can get my voltage around this one. Then for the current transformer, uh, we have a coil here, and then another low voltage coil, magnetic coil here. We can put it as a 0 to 5 ampere. This is a current transformer. Also, typical potential transformer like this, typical current transformer like this. This is a current transformer, potential transformer in a substation. So we can look more info from these references. So thank you.